Record. Good morning, everyone. Today is April the 24th. Welcome to the IME 470 class. First, let me stop the video and share my screen. Sure. Okay. The very first thing that I want to mention let me see, is I added one slide actually, excuse me, in lecture 11 for the MST. And so in the last lecture, we mentioned about this is the general formulation about MST. And here, I added one thing is that as the cardinality of S is greater than or equal to 2, that means you need to have at least 2 nodes. Otherwise, there's no edge to be IJ in ES. So let's have a look here. Where the example here's the example. So let's use a very small graph, for example. So here I have only 4 nodes. V is 1, 2, 3, 4, and your E set edge set is 1, 2, 3, 4. Your E set is actually all these sets 1, 2, 1, 2, 1, 3, 2, 3, 2, 4, and 3, 4. And again, in this lecture, we assume that all graphs are undirected. So if 1, 2 is an edge, then 2, 1 must be an edge. They're symmetric. Okay, first of all, the objective function here is what? Is the summation of, all the weights 1, 2, 4, 3, 10. All the weights times xij sigma. Xij equals to 1 if and only if ij, the edge ij, is inside, as in the minimum spanning tree. If xij equal to 0, that means it is not in the minimum spanning tree. Okay, so first of all, if you have a look at this one, so this tells you that the first constraint, this is actually for S equal to V, the same. It should be for all edges ij is in E, I must have xij, the sigma of them, is equal to n minus 1, where n is the number of nodes here. So have a look at here. In this example, my n equals to 3. So the right-hand side of the equation is 3. Sorry, my n equals to 4. So the right-hand side of the equation equals to 4 minus 1 equals to 3. And the left-hand side is what? The left-hand side is the summation of all edges versus their. I have a typo here. Well, I should not delete all this. I will update it after because I copy and paste. I forgot to delete all these kind of coefficients. There should be no weight coefficient here. It should just be x12 plus x13 plus x23 plus x24 plus x34 equals to 3. So this tells me that in the whole graph, the total number of edges included in the minimum spanning tree should be only 3. Again, the reason because as we mentioned the last time, that for 2 nodes, you should have 1. And then after adding 1 node, you're going to add one you are going to add 1 edge in the minimum spanning tree. And hence, the total number of edges included in the minimum spanning tree should be n minus 1. Okay. And after it, it's going to be what? It's going to be this the main constraint, which is for any subset of S in V, where S is not equal to V, S is not equal to empty set, and S the cardinality is at least 2, I should have this constraint. Okay, what does it really mean? Let's have a look at it here. So first of all, the power set means all the combinations of all subset. The all subset of the V. Total, I should have how many? I should have 16. Why this is actually all the possible combinations. For example, the subset of V can be empty set, or it can be V itself. This is V itself. And let's see, this is empty set. This is V itself. Oops, too big. This is V itself. And these 1, 2, 3, 4, these are the sets including 1 element, including 2 elements, including 3 elements, and totally, how many do we have? Including 1 element, we have 4 choose 1. Including 2 elements, we have 4 choose 2. Including 3 elements, we have 4 choose 3. Including 4 elements, we have 4 choose 4 plus an empty set 0, which is 4 choose 0. Okay, an empty set, which is 4 choose 0. So that what we have is actually this. What do we have is let me add it. What do we have? Okay, let me write it. Is actually C4 choose 0 plus C4 choose 1 plus C4 choose 2. Oh my God. I hope you can recognize. It's really not easy to use a mouse to write it. C plus C choose 3 plus C4 choose 4. C4 choose 4. And here, by the binomial equations, this simply equals to what? 2 to the power 4. Done. And actually, for any v, oh my God, for any v the same. If v is 1 to n, then the total number of subsets here, which is defined by the power set, the number of elements inside would be 2 to the power of n, which is a huge number. And that's also the reason why. And that's also the reason why I just use four nodes here, because if I have 5 nodes, then theoretically I could have as many as 32, which is too many. Okay, so here let's list them one by one. As we mentioned before, that we are not gonna include empty set. We're not gonna include v s equal to v itself. Empty set because it's meaningless to include. V s equal to v itself because what? Because here we go. The first element actually meaning the case for s equals to v. So, and also we're not gonna include include sets s with only 1 element. So all these gonna be removed. And hence, at most, we're gonna include these elements. And let's have a look one by one. Okay, first of all is s equal to 1, 2. So 1, 2 is here. For 1, 2, you're gonna have what? You're gonna have this. Let me go back. You're gonna have go back. Yes, you're gonna have this. The sigma of ij is in ES. Again, ES, I added something here. ES means the edges in the original graph composed by the nodes included in S, okay? Of xij is less than or equal to S1 minus the cardinality of S minus 1, okay? So first of all here, for S equal to 1, 2, your cardinality of S equals to 2, right? And then 2, sorry for the noise. I mean, they're doing something in the department now. Maybe they're making some new facilities, something. Anyway, so here your S equal to 1, 2. And hence your cardinality is 2. 2 minus 1 equals to 1. So the right-hand side is 1. Then the left-hand side should be what? Should be all the edge included in this subset composed of S. So see here, my subset is what? My current subset is, let me use this one, as 1, 2, right? So for the 1, 2, there's only 1 edge included here, which is x1, 2. And hence you have x1, 2 less than or equal to 1. This is for 1, 2. Now have a look at here, this one. So this one is done. Oops, Jesus. Can I make something a bit just, okay, let me use a circle to indicate. So this means it's done. Now let's have a look at the second one, which is which is edge 1, 3. So 1, 3 is here. What? Sorry, 1, 3 is here. This is 1, 3, right? And again, because your cardinality is 1, so right hand is 2, so the right hand side is 1 because cardinality minus 1, 2 minus 1 equal to 1. And here you have only 1 edge inside, which is x1, 3. So you have x1, 3 as less than or equal to 1. Okay, so the second one is also done. Now have a look at edge 1, 4. The question is what? The question is I don't have edge 1, 4. See it? The subset 1, 4 here. Have a look. Why? Because 1, 4, there's no direct link. No edge is included here, and hence I don't have anything. I'm gonna delete this. I don't have any constraint for 1, 4, the selection 1, 4. Okay, now have a look at. Now let's have a look at 1, 3. Let me see. This is gonna be deleted. For edge, for edge 2, 3. For H23, it's here. For the subset 2,3 is here. Again, the cardinality is 2, so the right-hand side is 1, and also, sorry, I'm talking about 1, 3, not 2, 3, not 2, 4. So, and also there's only one edge included inside. So I have x13 in the left-hand side. So you have x13 less than or equals to 4, equals to 1 for s equal to 1, 3. Okay, so here I'm done with 2, 3, not 1, 3, sorry, 2, 3. And then let's have a look at 2, 4, similar, see it? For the subset 2, 4, similar, I should have 2x24 less than or equal to 1. Okay, so I'm done with 2, 4. Then how about 3, 4? Similar, right? Because for 3, 4, I have only one edge, which is x34. So I have x34 is less than or equal to 1. Okay, done. And so here we go. For all these kind of subsets of S, including 2 elements, I'm done. Then consider these kind of subsets, including 3 elements. So the first thing we're gonna have a look at is is S equals to 1, 2, 3, which is here. Let me draw something. 1, 2, 3, and be careful. How many edges are included here? We have x12 and x23 and x13. See it? So that I'm gonna have this. I'm gonna have x12 plus x13, 23 plus x13 as less than or equal to 2. 2 is because the cardinality of S here equals to 3. So 1, 2, 3, you have 3 elements. So 3 minus 1 equal to 2, okay? And then, sorry about the noise. And then for the subset 1, 2, 4. 1, 2, 4 is here. 1, 2, and 4 is here. How many edges are included? I have x12 plus x24, right? And this should be less than or equal to 2. And again, 2 is because I have 3 elements. 3 minus 1 equal to 2. And then consider subset 1, 2, 4. 1, 2, 4 is done, sorry. Consider subset 1, 3, 4. 1, 3, 4 is here. Almost exactly the same, see it? Oops. 1, 3, 4 is right here. See it? So I should have x13 plus x34 is less than or equals to 2, which is here. Okay. And the final one is x234. And x234 is where 234 is here. How many edges are included? I have x23, I have x34, and I have x24. The sum of them should be less than or equal to 2. And here we go, this constraint. And finally, of course, do not forget the integer constraints, which is everything is in 0, 1. And here we go. That is the MST formulation, the whole thing here. Okay, clear everything. The whole thing here, this is the formulation of my MST for such a small graph. And you can see there are so many constraints for such a small graph. Now you realize the pain. What if I have 10 nodes? Theoretically, you can have as many as 1024 constraints. And it's a very, very baby graph that you have only 10 nodes, because in the real graph, you may have thousands of nodes, which is impossible for you to use this, for you to use this formulation, which is exponentially many, to list it. And that's also the reason why here we mentioned that we, in practice, in practical examples, nobody's gonna use this kind of formulation to really, formulate the MST problem. They are gonna use, for example, MTZ or hoop constraints. But these, 2 constraints need more time to introduce. Typically they're kind of grad, courses. They are listed in the grad course, and hence I didn't directly give you the solution. If you're interested, you please read these 2 papers. Or an easy thing is you directly just search them, and in Wikipedia you're gonna see it, which is a short version, and it's very simple. And the MTZ constraints and the hoop constraints are not required in this class, since it's an undergraduate class. That's everything I want to discuss today about lecture 11. Any questions about lecture 11? Any questions? You need to unmute yourself if you have a question because I set to mute everybody, in the beginning. No question? Okay. Now let's go to lecture 12. Oops, what lecture 12 is like this way? Is this lecture 12? Yes. Okay, now let's go to lecture 12. So in lecture so far for network optimization 1 and 2, we have introduced lecture 10 is network optimization 1, which is the formulations and a bit more applications about the shortest path problem. And the lecture 11, which is network optimization 2, we introduced the minimum spanning tree. And this is going to be the last lecture of network optimization and also the last lecture of the whole class, I mean for 70, which is the maximum flow problem and the minimum cut problem. Okay, so first of all, a very, very brief review for lecture 11, which is the concept of trees and also the definition of minimum spanning tree. And we also introduced the Prim's algorithm and the Kruskal's algorithm. And finally, we introduced the formulations for minimum spanning tree. Okay, so today we're going to introduce something about the maximum flow problem. For the maximum flow problem, first of all, let's have a look. What is the definition here? So consider a graph in this way. I have some numbers here indicated here, but they are not the weight anymore. They indicate actually the flow capacity. So the S here is our source and the T here is our sink node. S is the source node. And for each of these arc, be careful here. One thing is that I use arc instead of edge. So usually if the graph is a directed graph, then I'm going to use arc. And if the graph is an undirected graph, I'm going to use edge. Okay, so arc is more general than edge because edge means, if, for example, edge means, I don't have an edge here. For example, suppose 4 can go to 2. If it's an edge, that means 2 can go to 4 as well. But arc means no, it could be a one way rather than, always two ways. So here, what we are talking about arc. This is something different from the minimum spanning tree, in which we assume that all graphs in minimum spanning tree are actually undirected graph. Okay, so consider this graph, and we have an arc capacity here. Now the question here is how much at most can I transport the flow from S to T? This is something like a transportation problem, because, it's not infinitively many. Why? Because we can clearly see at most you can transport from S to T as 24 unit of, 24 units of the flow. Why? Because have a look here. At most, you can go from 2 to T plus 4 to T, which gives you the total flow of 20 plus 4, 24. So now the question is, the real number is how many can I transport from S to T? It's not just simply you say, okay, 20 plus 4 done. No. Because you need to guarantee how many you can totally transport from somewhere to 2. You see it? You can clearly see because 2 at most I can transport 12 plus 7, which is 19. So although the capacity is 20, it does not guarantee that you can really transport from 20 to 2 for 20 flows. You cannot transport 20 flows from node 2 to node T. Actually, the most for node 2 to T is only 19 because of this. And similar, for example, for node 4, I have a supply 14 at capacity 14 here. So for node 4, yes, and actually I only need to transport 11. Why? Because at most I can, send out 11 flows. So it's meaningless if I really transport, let's say, 14 flows, 14 units of flows from 3 to 4. So in general, suppose I give you a graph, which is GA, where V indicates the vertex set, and A indicates the arc set, then I have an arc capacity or flow capacity, which is Cij here. I use this notation. And also I added in parentheses here, so make it clear that it's actually a capacity rather than a weight. Then I'm asking, what is the maximum flow that can really you can transport from S to T? And this Cij indicates the maximum flow that can pass this arc. Okay. One thing I want to mention is the conservation of the total flow. That means no flow will be absorbed by passing a node or by passing an arc. However, the real story is that the conservation of the total flow does not apply. For example, consider this kind of power grid. Later, I think I do have an example about, actually, I'm gonna mention it. Let me see where. Something like this, the power grid. If you have heard something from physics or from some news, you're gonna see that in the power grid, the waste is huge. For example, the capacity of one arc, for example, is 100 units. Even if you really give 100 units, in this in this arc, the real number of the flow that can be transported, for example, from 3 to 4, might be only 30 or 40. It's a terrible, terrible, waste. Now we have some techniques to improve this, efficiency. However, it's still very, very low. But, in this lecture, we assume that no waste. In other words, no flows will be absorbed, or consumed by passing arc or nodes. Nodes similar. In the real life, the nodes could absorb flows. But here, let's assume that no, such absorbed activities and everything is going to be perfect. Okay, now the maximum flow, as we mentioned, is to transport the maximum flow from node S to node T, considering such flow capacities in each arc. So you may ask, what are the applications of this kind of problems? Yes, application one, very, very important things are this kind of power grid problem that I want to design, for example, a power grid in the whole United States, or let's make our life much smaller. Let's say in Fargo, which is around here, this area. And how would you design this kind of, the network? Or let's say based on the given network, how would you actually transport the power so that from A to B it's going to be maximum delivered. Another thing is, have a look at here. Suppose I want to deliver some power, for example, from California to, for example, let's say Arizona here, because California and the west and the east, usually it's you have more power because it's next to the ocean, but inside it's a bit more difficult. So you may want to generate a lot of power in the coast and then want to deliver it to some inner states. The question is, first, how to build a network. Second, based on the network that is already built, how would you transport to get the maximum delivery? So these are clearly maximum flow problems. And the second application is the flight crew scheduling. So suppose you're a manager of an airline company. You want to deliver flight crew from A to B, for example, from San Francisco to Atlanta, for example. Then the question is, how would you deliver at most? You may say, okay, easy. Let me just send a special flight and put all my crews there. Unfortunately, it doesn't work. First, in this case, you may cost too much because you need a specific flight. The real thing is that in many flights, it's not full. So that you can actually send some put 3 flight crews in this plane, put 2 flight crews in that plane. And indeed, I don't know whether you have seen, if you fly a lot, you're gonna see in many this kind of flights, you're gonna see some flight crews. They could be pilot, they could be just regular air hostess. And That's how it works in the real life. The problem is, how would you send maximum number of flight crews from A to B? And you need to consider that there's a limit. The limit of which is arc capacity. The arc capacity in the flight crew scheduling problem is what? Is the total number of seats minus the passenger orders. In other words, the empty seats. So it's not infinitively many. You can put, let's say, 1,000 people in the plane. No way, right? Usually it's just very little. Then how would you transport from A to B? And also you may need to consider that, for example, from ORD, I don't know what is ORD, Orlando? No, Orlando should be here. Miami, for example. Let's talk about Miami. For example, suppose you go this way from San Francisco to Los Angeles and then to Miami to Atlanta. Suppose you go this way, you need to consider that some flight crews may need to be transported from Miami to Atlanta as well. So how to really build a system that is going to consider all these problems, this kind of scheduling, maximum flow problem. And then not to mention this kind of traffic lights design or management. This is even more, because think about this. Suppose this is a traffic system. You can use the traffic lights to control the flows, right? Suppose, for example, there are too many cars. Let's say, suppose there are too many cars around here. What you're going to do is that you're going to try to, let's say around here, suppose from 2 to 3, it's very crowded. What you're going to do is what? You're going to probably use the traffic light to stop cars coming from other nodes to 2, and give the green in 2 and 3. So in this case, 2 and 3, cars going to get out, and no cars going to be incoming cars to 2, and hence it's going to be more free on the road, the street, let's say from 2 to 3. So that's how you can control the traffic. And the purpose is, for example, suppose this is a bridge system. You want to maximize the total number of traffic flows to go from S to 2. And hence, I can deliver the most cars, most traffic flows. And traffic flow is actually what? It's actually money. Why people build streets, why people build bridges? Because I want to make the traffic, I want to pass more cars, make the traffic easier. If the traffic flow is more, or I can pass more cars, that means what? That means in terms of economy, I can create more value. And that's the meaning. Actually, finally, everything is kind of like decision making, and actually everything is about values. Of course, it depends on how you define the term value. Anyway, so, and also here is a very, very old system in Soviet railway network in 1955. At that time, just finished the World War II, and it's the crowd. It's pretty crowded. It's their system, transportation system, that mostly, for example, they're gonna transport passengers and even troops, military troops, from A to B. And the Russia, it was Soviet. Soviet, was a huge country, very, 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 very big. And it's a big problem to build their railway system so that they can they can transport people from, for example, the east part to the west part maximum. And again, this is a maximum flow problem. Okay, we've mentioned so many applications and definitions about the maximum flow problem. Let's see how can we build a mathematical model, an accurate mathematical model actually here. First of all, this is pretty similar to shortest path problem, SPP. So here is a recall of SPP. Remember in SPP, what did we do? We mentioned that for node S, we have outflow equal to 1 and inflow equal to 0. And for node T, we have outflow equal to 0 and inflow equal to 1. And for intermediate nodes, we have inflow equal to outflow. Remember it? Let me open it. Wait, how can I get out? Let me see. Here we go. Lecture. Which lecture should be? Lecture 9, I think. Is it lecture 9? No. Lecture 10. In the shortest path problem, remember, we have, oops. Okay, for S, exactly 1 outflow. For T, exactly 1 inflow. And for intermediate nodes, we have inflow equals to outflow. See it? And here, single. And here you go. So this is for SPP. Actually, in MFP, maximum flow problem, it's very, very similar. But the difference is that you cannot assume that for node T, there's only 1 unit of outflow and 1 unit of inflow, because that's something we want to maximize. Okay, so the definition is here. Let xij to be the amount of flow transported on arc ij. Be careful here. When I say arc ij, that means it's directed from I to j. Okay, if I say edge ij, that means it's, it doesn't matter I to j or j to I. But here, we'd better say arc ij because there's no guarantee it's bidirected or undirected. The graph could be directed. So that means from I to j, it's not equivalent to from j to I. And then let's use x0 to denote the total flow transported from S to T. And immediately, by definition, maximum flow problem. What I want to do to maximize this x0, see it? Because x0 is the total flow transported from node S to node T, and I want to maximize the total transportation, and of course I want to maximize the x0 here. Okay, now it's clear using the same idea that we used in the SPP. For node S, I have what? I have x0 is the total number transported, right? And from S, you can go to where? You can go to nodes 1 and 3. So immediately I have I have x0 equals to xs1 plus xs3. Okay, so here we go. xs0 equals to xs1 plus xs3. This is for node T, node 0. Then how about for node T? From which nodes you can go to T? Clearly, I can go from 2 to T or 4 to T. That's it. I don't have the third choice. And hence, I have x2t plus x4t, but be careful here. Oops. Be careful here. I should have this one equals to x0. Why equals to x0? Rather than, for example, as we mentioned in for example, shortest path, for example, equal to another number. Let's say I find a new notation, for example, xt or whatever. Why I can use x0? Because of what? Because of this, the law of conservation. Because there's no, consumption or this kind of absorbed, flows by passing a node or an arc. So I can guarantee that as long as this S is reasonable, this x0 is reasonable. Reasonable means, for example, I don't have to send more than 19 flows to 2. Why? Because the total number to 2 is at most 12 plus 7, right? And finally, you're going to see the solution, because finally, we're going to solve this problem, and you're going to see the real answer, the final answer of this. So this XS means everything is going to be reasonable, and everything's going to be perfectly used. And hence, I can guarantee that as long as I send x0 flows out from S, all of them, 100% of them, will be transported to node T. And hence, I have the total incoming flows equal to x0 equals to the total outflow, or let's say the incoming flow to T. So everything 100% will be transported to T. And hence, I have x4t, and hence I have x4t plus x2t equals to x0, which equals the flow from S. Okay, so these are the constraints for nodes S and T. And for all intermediate nodes, I should have inflow equal to outflow, which is exactly the same as here as the SPP. So for example, for node 1, we have what? What are the inflows for node 1? I have S1. I also have 3,1, right? This should be equal to the outflow from 1. That is 1,2 plus 1,3, so that you have xs1 plus x31 equals to x13 plus x12. How about for node 2? Similar. For node 2, the inflows are x12, x42, and outflows are x23 and x2t, right? So this is for node 2. How about node 3? Similar. For node 3, the incoming is 23, 13, and S3. I have 3 incoming. And the outgoing from 3 is x31 and x34. So that you must have xs3 plus x13 plus x23 equals to x31 plus x34. Okay, and finally for node 4, node 4 I only have, let me see, only 1 incoming, which is x34. For outgoing flows, I have x42 and x40. So finally, you have x34 equals to x42 plus x40. And after this, do not forget to add all these constraints. This tells me the arc capacity, Xij, must be less than or equal to Cij. This Cij means the numbers here. So for example, you should have xs1 is less than or equal to 16, xs3 is less than or equal to 13, x13 is less than or equal to 10, blah, blah, blah. List this for all these arcs, okay? And now let's have a look at the complete model for this specific graph. Oops, you should have this. As we just mentioned, so first of all, this is for node S, for node T, and here they are for intermediate nodes that we just mentioned, and these are the arc capacities, which is you're gonna list all the arcs xs1, S3, and then x13, and then x31, and then 1, 2, 2, 3, 3, 4, 4, 2, 2t, 4t, list all these capacities. And finally, you're gonna have what? Finally, you're gonna have x0 and xij is greater than or equal to 0, of course, because the flows are non-negative. And then I'm gonna use Excel to solve this problem. Okay, so this is the model about maximum flow problem. Are there any questions? Any questions here? No question? Okay, then let's try to solve this problem. You see it? So let me see here. Okay, so here I have xs1, xs3, x13, x31, x12, x23, x34, x42, x2t, 2t, x4t. Let me see. Okay, total of 10 in case I make any stupid mistakes. And let me put the limit here, the capacity here, 13, 10, 4, 12, 9, 14, 7, and 20, and 4. Okay, these are the capacities. Okay, the objective function, I forgot the most important one, which is x0. Okay, the objective function is this, is equal to x0. That I'm gonna maximize it. And then constraints. First, the constraint is gonna be, okay, let's say for x0, for xt, and then for x1, for x2, let me see whether the Excel is smart enough. For x3, great. Okay, so let's see the constraints for x0 as I should have x0 minus xs1 minus xs3 equal to 0. For xt, I should have x4t plus x2t. Where's my x2t? My x2t minus x0 equal to 0. And for x1, I should have what? I should have xs1 plus x31 minus x13 minus x12 equal to 0. And for x2, I should have what? Where's my x2? It's here. x12 plus x42 minus x23 minus x2t equal to 0. And for x3, I'm looking here. For x3, I should have xs3 plus x13 plus x23 minus x31 minus x34 equal to 0. And the last one is x34 minus x42 minus x40 equal to 0. 40 equal to 0. Okay, great. Then let's go to Excel solver to solve it, to see what's going to happen. Data, Excel solver. Okay. So I want to maximize this one, and then changing variables are here, and everything are non-negative. So this guarantees that everything is non-negative. Let me use simplex method, adding constraints. First of all, you need to add all these things are equal to 0. And do not forget to add these, okay? All of them should be less than or equal to this, okay? And solve. And see the solution? The solution is, okay, let me make it a bit bigger so that you can see more clear. So the solutions are here. Okay, so the maximum flow is going to be what? It's going to be 23. And let's decompose the maximum flow to be the final answer. So, oh my God, please be smaller. So in S1, S1, I should have 12 units. Let me see what I can control the paste. I cannot. And here, Jesus, can you be a bit smaller, please? In S3, I should have 11. Okay, so total I have 12 plus 11. And then let's see, how does this 12 and 11, really decomposed? So here from x13 is 0, 13 here is 0. Okay, let me open this. This is too slow. Let me go 1 second. Let me open the Excel here. Lecture this one. 12. I should have a PowerPoint here. Yes, I have a PowerPoint here. Let me do one thing, make my life easier. Create a new one. Okay. And then let me just delete everything else. I just need this graph. That's it. Oops. Come on. Okay, now let's have a look at the solution here. Then I think it's going to be easier for us to do something. Okay, so here our solutions are bigger. Our solutions here are, let's say, here x12 is 12. Oh no. Let me use a red color, for example, and don't need 18. Make it to be, for example, 14. Make it more clear. So here x1 is 12. And then I can copy and paste. Great. And xs3 is what? Is 11. And my x13 is what? X13 as 0. And my x31 is also 0. And you can see what? In this route, 1, 2, 3, or 3, 2, 1, I do not pass it. I directly go this way probably. Okay, let's see. And then x12 is 12. So I send everything here and here. And now we can know why it is 12 instead of 16. because it's not going to be wasted. See it? If I, for example, transport 13, it doesn't work because here is 12. The maximum flow here, capacity of arc 1, 2 is 12. So even if you transport 13, it doesn't work. People may say, hey, why don't I, for example, transport, for example, 13 and the 12 here, 1 unit here? And you're going to see why, because here I have 11. And here, see it? 9, this is probably going to be 9, and this is going to probably be 3, and here we go. In other words, if you transport 13 here, it's still going to be wasted because here the maximum capacity is 14. Let's see it. X1, 2 is 12, and then X2, 3 is 0. And then X3, 4 is 11. 3, 4, 3, 4, 3, 4 is 11. And then X4, 2 is 7. 4, 2 is 7. 2T is 19. And then finally, 4T is 4. Okay, great. Okay, so this is the final optimal solution of this problem. And you can clearly see how does it deliver. Let me use a color, let's say red color, and the arrow here. So I first transport 12 units here. And these 12 units, the distribution will be all of them come here, come to 2. And so now I'm not going to transport any flow from 2 to 3. And all these 12 is going to go to T. Okay. On the other hand, I have 11 flows from S to 3. And these 11 flows, all of them are going to be here. Then how to distribute or decompose this 11? 4 of them will be sent to T, and another 7 flows going to be sent to 2. And that's the reason why from 2 to T, I have a 12 plus 7 equal to 19 flows. See it? And hence my final final flow transported to T is gonna be let me directly copy and paste, make my life easier. So maximum flow transported will be X0 equal to 23. Here we go. And that's the solution to the problem. Okay. Any questions here regarding this problem? Any questions? No question? Okay. I think that's now. What's the time now? Now it's almost 9:50. Okay. Very good. I think that's the thing that I wanna discuss for today. Thank you very much for today's lecture, and see you next Monday. Have a good weekend. Bye bye.